For decades, we believed black holes were the ultimate destroyers, regions of space-time so warped by gravity that nothing, not even light, could escape their pull. Einstein's equations predicted them in 1915, and by the 1960s, physicists confirmed that when massive stars collapse, they create objects of infinite density, crushing everything into singularities where the laws of physics break down. But here's what will blow your mind. It's wrong. Every black hole might not destroy universes, but birth them. The moment matter crosses an event horizon, it doesn't collapse into nothingness. It explodes outward into an entirely new cosmos, complete with its own galaxies, stars, and perhaps even intelligent civilizations. This isn't speculation. This is mathematics. And if it's true, our universe might exist inside a black hole. And every black hole in our cosmos might harbor infinite realities we can never reach. If you want to discover how death becomes creation and collapse becomes explosion, hit that like button and subscribe. Prepare yourselves. Let's begin. The story of how we arrived at this extraordinary conclusion begins with the simplest object in relativistic physics, the Schwarzschild black hole. In 1915, just months after Einstein published his general theory of relativity, Karl Schwarzschild solved Einstein's field equations exactly while serving on the Russian front during World War I. He found something Einstein himself didn't expect, a solution describing an object so dense that space and time switch roles at a critical radius. This boundary, now called the event horizon, marks the point where escape velocity equals the speed of light. Fall past that threshold, and returning becomes physically impossible. Not difficult, impossible. The geometry of space-time itself prevents it. For 50 years, most physicists, including Einstein, didn't believe such objects could actually form in nature. They seemed too extreme, too pathological. Surely nature would find a way to prevent complete gravitational collapse. But in 1967, John Wheeler coined the term black hole. And by the 1970s, observational astronomy had detected Cygnus X1, the first confirmed stellar mass black hole. It was real. Stars more massive than about 20 times our Sun do collapse when their nuclear fuel runs out. The core implodes in less than a second. If the remnant exceeds about 3 solar masses, no force in nature can stop the collapse. Neutron degeneracy pressure fails. Quark matter can't support it. The star crosses its Schwarzschild radius and forms an event horizon approximately 3 kilometers per solar mass. A 10 solar mass black hole has an event horizon about 30 kilometers across. Sagittarius A star, the supermassive black hole at the center of our Milky Way, contains 4.1 million solar masses and has an event horizon approximately 12 million kilometers in diameter, 16 times the size of our Sun. These numbers represent boundaries in space-time. Cross them, and according to classical general relativity, your fate is sealed. The equations predict you'll hit the central singularity in finite proper time. For a stellar mass black hole, that's less than a millisecond. For Sagittarius A star, you'd have about 15 seconds. And at the singularity, the curvature of space-time becomes infinite. Density becomes infinite. Volume becomes zero. The mathematical description of reality produces infinities, which in physics typically signals that the theory has broken down, that we're extrapolating beyond its domain of validity. This is where quantum mechanics enters the story. Quantum theory fundamentally forbids infinite densities and zero volumes. At scales approaching the Planck length, 10 to the negative 35 meters, quantum uncertainty dominates. The Heisenberg uncertainty principle prevents you from localizing anything, even space-time itself, below that scale. Trying to probe smaller distances requires such enormous energies that you'd create black holes, which makes the measurement impossible. This sets a fundamental limit. You cannot compress matter into a mathematical point. Quantum effects must intervene. But general relativity, which describes black holes, is entirely classical. It doesn't include quantum mechanics at all. So when we calculate what happens at the center of a black hole using Einstein's equations alone, we're using a theory we know must fail under exactly those conditions. For decades, physicists avoided this problem through cosmic censorship. The idea is simple. Whatever quantum weirdness happens at the singularity, it's hidden behind an event horizon. We can never observe it from outside. The universe protects us from seeing the breakdown of physical law. This was philosophically uncomfortable but pragmatically acceptable. As long as singularities remained invisible, we could acknowledge the problem without needing to solve it immediately. But some physicists refused to accept this. They wanted to know what actually happens, not what the equations say when pushed beyond their limits, but what nature actually does when quantum mechanics and general relativity both apply with full force. Loop quantum gravity provided an answer. This approach attempts to quantize spacetime itself, treating it not as a smooth continuum, but as a network of discrete quantum connections at the Planck scale. When you apply loop quantum gravity to gravitational collapse, something remarkable happens. As matter compresses toward the Planck density, about 10 to the 93 grams per cubic centimeter, quantum repulsion becomes stronger than gravitational attraction. The collapse stops, then reverses. The matter bounces. This isn't speculation. It's a prediction that emerges directly from making spacetime quantum mechanical. The singularity never forms. Instead, you get a quantum bounce. But here's the crucial part. The bounce doesn't send matter back out through the event horizon. The spacetime geometry is too warped for that. Instead, the rebounding matter expands into a new region of spacetime, geometrically connected to the original universe only through the narrow throat of the black hole. From outside, in the parent universe, this process is invisible. The event horizon forms. Matter falls in and disappears from our observable reality. Nothing comes back out. The black hole behaves exactly as classical general relativity predicts. But from inside, the quantum bounce looks completely different. It looks like a big bang, an explosive expansion of space and matter from an extremely hot, dense initial state. The formation of a new universe. Think carefully about the implications. Every stellar mass black hole in our galaxy, and there are approximately 100 million of them, would not be an endpoint. Each would be a seed, a portal, a transition point between one cosmic domain and another. The matter that falls through the event horizon, carrying energy and angular momentum and quantum information, doesn't vanish. It becomes the initial conditions for a new expanding universe. From our side, we see a black hole. From the other side, they see their cosmic origin. Their Big Bang is our black hole formation. Their moment of creation is our moment of collapse. This completely inverts our understanding of black holes. They're not cosmic graves. They're cosmic wombs. Not the death of structure, but its most profound rebirth. And the mathematics describing this doesn't require any exotic additions to known physics. Just quantum mechanics applied where quantum mechanics must apply, at densities where classical descriptions break down. The equations of loop quantum gravity, combined with Einstein's field equations, naturally produce this behavior. You don't add it by hand. It emerges from taking both theories seriously in their respective domains and following the implications to their logical conclusion. To understand why physicists now believe black holes might contain universes, we need to understand what Einstein's theory actually predicts. And the answer is both elegant and disturbing. General relativity describes gravity not as a force, but as curvature of space-time itself. Mass and energy warp the fabric of space and time, and objects moving through that warped geometry follow curved paths we perceive as gravitational attraction. The more massive an object, the more it curves space-time around it. For most objects, this curvature is gentle. Earth curves space-time enough to keep us on its surface and the Moon in orbit. The Sun curves it enough to hold the entire solar system together. But these are small perturbations compared to what's possible. Einstein published his field equations on November 25, 1915, in a paper titled The Field Equations of Gravitation, to the Prussian Academy of Sciences in Berlin. These 10 coupled nonlinear partial differential equations relate the curvature of space-time, expressed mathematically by the Einstein tensor, to the distribution of mass and energy, expressed by the stress-energy tensor. They tell you how matter curves space-time and how that curvature affects the motion of matter. They're notoriously difficult to solve. Einstein himself never found an exact solution to his own equations for any realistic physical scenario. But Karl Schwarzschild did. While serving as an artillery officer calculating trajectories on the Russian front during World War I, just months after Einstein published his theory, Schwarzschild found an exact solution describing the space-time geometry outside a spherically symmetric non-rotating mass. He sent the solution to Einstein in December 1915. Einstein was astonished. He presented Schwarzschild's result to the Prussian Academy in January 1916, calling it an important contribution. Schwarzschild died of a disease contracted at the front just 4 months later, at age 42, never knowing how profoundly his solution would reshape our understanding of the cosmos. The Schwarzschild solution reveals something extraordinary. For any mass, there exists a critical radius, where space-time curvature becomes so extreme that the roles of space and time exchange. This radius, now called the Schwarzschild radius, equals 2 times the gravitational constant times the mass divided by the speed of light squared. For the Sun, it's about 3 kilometers. For Earth, it's 9 millimeters. As long as the actual physical radius of an object exceeds its Schwarzschild radius, nothing dramatic happens. The Sun is 700,000 kilometers across, vastly larger than 3 kilometers, so its Schwarzschild radius sits deep inside its interior, where the solution doesn't apply anyway. But if you could compress the Sun down to a sphere 3 kilometers in radius, or Earth down to the size of a marble 9 millimeters across, something radical occurs. At the Schwarzschild radius, the escape velocity equals the speed of light. This isn't a problem with rocket fuel or propulsion technology. It's a fundamental consequence of space-time geometry. Inside this boundary, called the event horizon, all future directed time-like paths point inward toward the center. You cannot move outward because outward is no longer a direction in your future. It's in your past. Space and time have exchanged roles. The radial direction has become time-like, meaning moving inward is as inevitable as moving forward in time. You will reach the center just as surely as you will reach next Tuesday. There's no escape. Not because gravity is pulling too hard, but because the geometry of space-time itself makes outward motion impossible. This is what makes black holes fundamentally different from any other object in the universe. It's not about strength, it's about topology, about the causal structure of space-time. Once you cross an event horizon, you are no longer in causal contact with the exterior universe. No signal you send, no particle you emit, no information you encode can ever reach someone outside. From their perspective, you appear to freeze at the horizon, your image redshifting and dimming exponentially, fading from view over infinite time. But from your perspective, you cross in finite time, typically seconds or less, and nothing about the local environment alerts you that you've passed the point of no return. Space still looks like space. Time still flows forward, but your future now terminates at the center. And what happens at the center is where Einstein's theory breaks down completely. The Schwarzschild solution predicts a singularity at radius equals 0. At this point, space-time curvature becomes infinite. Density becomes infinite. The mathematical description produces meaningless infinities. Roger Penrose proved in 1965, work for which he won the 2020 Nobel Prize in Physics, that once a trapped surface forms, a surface where all light rays converge inward, the formation of a space-time singularity is inevitable, according to general relativity. You cannot avoid it. The geometry forces you toward it. Penrose's singularity theorem requires only minimal assumptions. The weak energy condition, which says energy density is always positive, and the existence of a trapped surface, which occurs generically during gravitational collapse. Given those conditions, a singularity must form. Stephen Hawking extended Penrose's work backward in time. If singularities form inevitably in collapsing matter, and if we run the expansion of the universe backward, the same mathematics applies. Hawking's singularity theorem, published in 1967, proved that the Big Bang itself must have been a singularity if general relativity holds all the way back to the beginning. These theorems are mathematically rigorous. They follow inevitably from Einstein's equations. They revolutionize cosmology and black hole physics. But they also revealed a fundamental problem. Singularities represent the failure of general relativity. When a physical theory predicts infinities, it's telling you it no longer applies. It's reached the boundary of its domain of validity. You're extrapolating beyond where the model can be trusted. For most of physics history, this was acceptable because singularities hide behind event horizons. We cannot observe them. Cosmic censorship, the conjecture that singularities never form naked, visible to the exterior universe, protects us from seeing the breakdown of physical law. Whatever happens at the singularity remains locked away, causally disconnected from our reality. So while the mathematics fails, the predictions we can actually test remain finite and well-defined. But this is intellectually unsatisfying. Nature doesn't produce infinities. Infinities are artifacts of incomplete theories, and we know general relativity is incomplete because it doesn't include quantum mechanics. At extreme densities and small scales, quantum effects must dominate. The Heisenberg uncertainty principle prevents localizing particles or even spacetime itself below the Planck length, approximately 10 to the negative 35 meters. At this scale, quantum fluctuations of spacetime geometry become significant. Space and time become uncertain, foamy, probabilistic. You cannot compress matter into a mathematical point because quantum mechanics forbids definite positions at arbitrarily small scales. Trying to localize something that precisely requires enormous energy, enough to create a black hole, which prevents the measurement. There's a fundamental limit. So when general relativity predicts matter compresses to infinite density. At radius equals 0, we know this cannot be physically correct. It's what the equations say when pushed beyond their applicable regime. What actually happens must involve quantum gravity, a theory combining general relativity and quantum mechanics that we don't yet fully possess. But we have candidates. Loop quantum gravity, string theory, and other approaches all attempt to describe what happens when both quantum effects and gravitational curvature are strong. And they all predict something different from classical singularities. They predict quantum bounces, quantum foam, Planck scale structures, not infinities, not mathematical breakdowns, but new physics. Physics that prevents singularities from forming and replaces them with something finite, something quantum mechanical, something that might, just might, look like the birth of a new universe. This is where the story gets interesting. Because once you accept that quantum effects prevent singularities, once you acknowledge that something else happens at the center of black holes, you're forced to ask what that something is. And when physicists calculated the answer using loop quantum gravity, applying quantum mechanics to the fabric of spacetime itself, they found that collapsing matter doesn't stop at a point. It bounces. And that bounce, occurring in a region of spacetime already sealed off from the external universe by an event horizon, looks from the inside exactly like a Big Bang, the birth of an expanding cosmos, a universe within a black hole. Not speculation, not philosophy, mathematics, and it changes absolutely everything. The problem with singularities isn't just that they're mathematically inconvenient. It's that they represent the complete and total failure of physics to describe reality. At a singularity, every physical quantity we use to make predictions becomes infinite or undefined. Density becomes infinite. Curvature becomes infinite. Temperature becomes infinite. The equations produce numbers that have no physical meaning. This isn't a small error we can correct. It's a sign that the theory has reached its absolute limit and cannot be trusted to describe what happens next. For decades, physicists convinced themselves this wasn't a crisis because singularities hide behind event horizons. Roger Penrose formalized this intuition in 1969 with his cosmic censorship conjecture. The hypothesis states that nature abhors naked singularities, singularities visible to the external universe. Every singularity that forms from realistic gravitational collapse will be surrounded by an event horizon that prevents us from observing where the physics breaks down. Whatever mathematical horrors occur at the center of a black hole, they remain causally disconnected from our reality. We can never see them. We can never receive information from them. So while they might offend our theoretical sensibilities, they don't actually threaten our ability to make predictions about observable phenomena. But cosmic censorship only hides the problem. It doesn't solve it. Nature still needs to do something at the center of a black hole. Matter that crosses the event horizon has to go somewhere, has to do something, has to obey some laws, even if those laws aren't the ones we currently understand. And this is where quantum mechanics becomes absolutely unavoidable, because quantum mechanics sets fundamental limits on how small, how dense, and how localized anything can be. The Heisenberg uncertainty principle, discovered in 1927, states that you cannot simultaneously know both the position and momentum of a particle with arbitrary precision. The more precisely you determine one, the more uncertain the other becomes. This isn't a technological limitation. It's a fundamental property of quantum systems. Position and momentum are conjugate variables. They don't have definite simultaneous values. The universe itself doesn't contain that information. This principle has profound implications for black holes. To compress matter to infinite density requires localizing it to zero volume. But localizing a particle to smaller regions requires increasing momentum uncertainty. At scales approaching the Planck length, about 10 to the negative 35 meters, the momentum uncertainty becomes so large that the energy uncertainty exceeds the mass energy needed to create a black hole at that scale. You cannot probe smaller distances because the act of probing creates a black hole that prevents the measurement. This sets an absolute lower limit on meaningful spatial distances. Below the Planck length, the concept of distance itself becomes ill-defined, dissolved into quantum foam where space-time itself fluctuates probabilistically. The Planck length emerges naturally from combining three fundamental constants of physics: the gravitational constant, g, the speed of light, c, and Planck's constant h bar. It equals the square root of g times h bar divided by c cubed, approximately 1.6 times 10 to the negative 35 meters. This is 20 orders of magnitude smaller than a proton. At this scale, quantum fluctuations of the gravitational field become as strong as the field itself. Space-time ceases to be a smooth continuum and becomes a seething quantum foam of virtual black holes and wormholes. The Planck density, the mass contained in a cubic Planck length, equals approximately 10 to the 93 grams per cubic centimeter. For comparison, atomic nuclei have densities around 10 to the 14 grams per cubic centimeter. Neutron stars reach about 10 to the 15. The Planck density exceeds all of these by factors of 10 to the 78th power or more. It represents the absolute extreme of matter compression before quantum mechanics forbids any further squeezing. Here's the crucial point. General relativity predicts that matter at the center of a black hole compresses past the Planck density, all the way to infinite density at a mathematical point. But quantum mechanics says this is impossible. The uncertainty principle prevents localizing matter to arbitrarily small volumes. Something has to give. And since general relativity is a classical theory that doesn't include quantum effects, while quantum mechanics has been tested to extraordinary precision and never failed, the logical conclusion is that general relativity's prediction of singularities is simply wrong. It's an artifact of using a classical theory beyond its domain of validity. So what actually happens? This is the question that has driven theoretical physics for half a century. What replaces the singularity? What does nature do when you compress matter to Planck densities inside an event horizon? For a long time, physicists didn't have tools to answer this. Quantum field theory works beautifully on fixed space-time backgrounds. But inside a black hole, space-time itself is dynamical, warped, and collapsing. You need a theory of quantum gravity, a framework that treats space-time itself quantum mechanically. We have candidates. Loop quantum gravity takes space-time itself and quantizes it, treating it not as a smooth continuum, but as a network of discrete quantum connections at the Planck scale. String theory replaces point particles with tiny vibrating strings and requires extra spatial dimensions. Both approaches make predictions about what happens at Planck densities. And remarkably, despite their very different starting points, they agree on one crucial point. Singularities don't form. Quantum effects intervene before density reaches infinity and prevent the collapse from continuing. In loop quantum gravity, this intervention takes a specific form called a quantum bounce. As matter collapses and density approaches the Planck scale, quantum repulsion, arising from the discrete structure of space-time itself, becomes stronger than gravitational attraction. The collapse halts, then reverses. The matter bounces. This isn't a physical force in the classical sense. It's a consequence of space-time geometry becoming quantum mechanical. At Planck scales, the smooth geometry that Einstein's equations describe dissolves into discrete quantum chunks. These chunks cannot be compressed further. They have a minimum volume set by quantum mechanics. When matter tries to collapse past this threshold, the quantum structure of space-time resists, generating an effective repulsive pressure that stops and reverses the collapse. Think about what this means physically. An observer falling into a black hole would experience a smooth passage through the event horizon. Nothing local alerts you to crossing that boundary. For a supermassive black hole, tidal forces at the horizon are negligible. You wouldn't even notice. But as you continue falling inward, approaching the region where classical theory predicts a singularity, quantum effects become dominant. Instead of hitting a singularity, where density and curvature diverge to infinity, you encounter a quantum bounce where matter reaches Planck density, stops contracting, and begins expanding. And here's where the story becomes extraordinary. The bounce doesn't send you back out through the event horizon. The geometry doesn't allow it. Once you've crossed that boundary, all future directed paths lead inward. But space-time inside a black hole is so warped that when the quantum bounce occurs, matter doesn't expand back into the universe that formed the black hole. It expands into a new region of space-time, connected to the original only through the narrow throat of the black hole. From outside, the black hole appears stable. But inside, beyond the point where quantum gravity takes over, a new space-time region inflates. A new universe is born. And from inside that universe, looking backward in time, the quantum bounce looks exactly like a Big Bang. In 1992, physicist Lee Smolin published a radical paper that would transform how we think about the relationship between black holes and universes. He called it cosmological natural selection, and it remains one of the most daring and testable theories about why our universe has the specific properties it does. The core idea is simple but profound. If every black hole spawns a new universe with slightly different physical constants, and if those new universes produce their own black holes, then over countless generations, the multiverse would evolve to favor universes optimized for black hole production. Just as biological evolution selects for organisms best suited to reproduce, cosmological evolution would select for universes best suited to create black holes. Think about what this means. Our universe contains approximately 21 fundamental constants: the mass of the electron, the strength of the strong nuclear force, the cosmological constant. These numbers aren't predicted by theory. They're measured experimentally and plugged into our equations. Why do they have the specific values we observe? The traditional answer invokes the anthropic principle. These constants must have life-permitting values, because if they didn't, we wouldn't exist to ask the question. But this explains nothing. It just restates the observation. Smolin proposed something far more powerful. These constants have the values they do because universes with these values produce more black holes than universes with slightly different values. Universes that produce more black holes have more offspring, more descendants in the next generation of the cosmic family tree. Over time, through Darwinian selection, the multiverse becomes dominated by universes with constants optimized for black hole formation. We don't live in a randomly selected universe. We live in a universe descended from a long line of black hole-producing ancestors, inheriting constants refined across billions of generations to maximize stellar collapse. This is testable. If Smolin is right, then small changes to any fundamental constant should decrease the number of black holes the universe produces. Change the electron mass slightly, and stellar evolution should produce fewer black holes. Change the strength of gravity, and either stars don't form or they collapse into configurations that don't favor black hole production. The theory makes a falsifiable prediction. Our universe should sit at a local maximum for black hole production. Any direction you move in parameter space, black hole formation becomes less efficient. Initial tests have been promising. Physicist Fred Adams and others have calculated how black hole production varies with changes to fundamental constants. For many parameters, our universe does appear near a local maximum. Change the mass of the up quark by more than a few %, and you lose stable carbon, which disrupts stellar nucleosynthesis and reduces black hole formation. Change the gravitational constant, and you alter the balance between stellar lifetimes and collapse conditions. Our universe threads a narrow path through parameter space where stars form abundantly, live long enough to produce heavy elements, and collapse efficiently into black holes. The mechanism requires 3 ingredients, precisely analogous to biological evolution. First, reproduction. Black holes must spawn new universes. We've discussed how quantum gravity predicts this through quantum bounces at Planck densities. Second, variation. The constants in offspring universes must differ slightly from the parent. This is the most speculative part. Smolin proposes that quantum fluctuations during the bounce randomly perturb fundamental constants. The Planck scale physics that prevents singularities might also reset particle masses and coupling strengths, creating new universes with parameters clustered near but not identical to parent values. Third, selection. Universes that produce more black holes have more offspring. This follows automatically. If each black hole creates one new universe, then a universe forming 10 trillion black holes has 10 trillion descendants. A universe forming only 1 million black holes has 1 million descendants. After many generations, the multiverse population becomes dominated by lineages descended from prolific black hole producers. Constants that maximize black hole formation spread through the population, not because they're special or designed, but because universes with those constants simply have more offspring. The beauty of this framework is that it explains fine-tuning without invoking design or observer selection. We don't need a designer who chose these constants to allow life. We don't need the weak anthropic principle. Instead, constants are selected for black hole production, and it turns out that universes good at making black holes are also good at making complex chemistry, stable stars, and long-lived environments where life can emerge. Life is a byproduct of optimization for reproduction at the cosmic scale. Consider stellar mass black holes. They form from stars between roughly 20 and 60 solar masses. Too small, and the remnant becomes a neutron star. Too large, and pair instability supernovae might completely disrupt the star without leaving a remnant. Our universe produces stars across a wide mass range, generating millions of massive stars per galaxy that eventually collapse into black holes. The metallicity of the universe affects this process. Too little metal content, and stars burn hotter and might not produce black holes efficiently. Too much, and stellar winds might strip away mass before collapse. Our universe has evolved to a metallicity that supports robust black hole production. Supermassive black holes add another channel. They exist in most large galaxies, some containing billions of solar masses. If these also spawn universes, they represent extremely massive offspring events. A universe that efficiently forms supermassive black holes would have enormous reproductive advantage. Our universe does form them, and does so in ways that correlate with galaxy evolution. The mass of a galaxy's central black hole scales with the mass of its bulge. This suggests deep connections between structure formation and black hole production. The theory makes another striking prediction. The constants shouldn't just favor black hole formation, but maximize it. We shouldn't be able to tweak any constant to significantly increase production. Calculations suggest this holds for many parameters, but the cosmological constant presents a puzzle. Its observed value is tiny, allowing the universe to expand slowly and form structures over billions of years. A larger value would accelerate expansion too quickly, preventing galaxy and star formation, drastically reducing black holes. So our small cosmological constant fits the theory. But could it be even smaller and produce more black holes? This remains an open question that could potentially falsify Smolin's proposal. Cosmological natural selection transforms black holes from cosmic graves into cosmic wombs and evolutionary engines. They're not just endpoints of stellar death, but mechanisms of universal reproduction and drivers of a selection process that shapes fundamental physics across generations of universes. We're not living in a universe with arbitrary constants. We're living in a universe descended from countless ancestors, shaped by eons of cosmic evolution to excel at one thing above all: creating more universes. Lee Smolin's cosmological natural selection provides an evolutionary framework, but it doesn't explain the physical mechanism connecting parent and offspring universes. How does matter actually transition from one universe to another through a black hole? This is where Nikodem Poplawski's work becomes crucial. In a series of papers beginning in 2010, this Polish theoretical physicist proposed that black holes function as Einstein-Rosen bridges, wormholes connecting different regions of spacetime. Matter doesn't collapse to a singularity. It passes through a tunnel and emerges as the raw material for galaxies, stars, and planets in another reality. The key insight involves torsion, a geometric property of spacetime that Einstein's original theory neglected. General relativity describes spacetime curvature, but assumes the affine connection. The mathematical structure describing how vectors change as they're transported through curved space is symmetric. This works beautifully for most situations. But when you include spinning matter, particularly the intrinsic spin of fermions, like electrons and quarks, the mathematics requires an antisymmetric component. This is torsion. Just as curvature describes how parallel lines converge or diverge, torsion describes how vectors twist and rotate as they move through spacetime. Torsion couples to spin. For ordinary matter at ordinary densities, this coupling is negligibly weak. You'll never detect torsion effects in laboratory experiments or even in the strong gravitational fields around neutron stars. But at Planck densities, when fermionic matter compresses to the point where quantum effects dominate, torsion becomes significant, and it generates something remarkable. Gravitational repulsion. The same spin-torsion coupling that's irrelevant at low densities becomes a powerful repulsive force at extreme compression. As matter collapses inside a black hole and approaches Planck density, this repulsion halts the collapse. No singularity forms. Instead, the matter bounces. But Poplawski's calculations reveal something Einstein-Rosen bridge theory predicted decades earlier. The bounce doesn't occur at a point. It occurs throughout a region of spacetime with non-trivial topology. The extreme curvature created by the collapsing matter warps spacetime so severely that the interior of the black hole connects to a different spacetime region through a bridge, a tunnel, a wormhole. From the perspective of the parent universe, the black hole has an event horizon beyond which nothing returns. From the perspective of the bridge interior, spacetime extends through a throat and opens into an expanding region on the other side. This other side experiences the bounce as explosive expansion. A Big Bang. The matter that fell through the event horizon provides the initial mass energy. The angular momentum of the collapsing star becomes the primordial rotation that might seed large-scale structure. The extreme conditions in the throat region, where torsion prevents singularity formation, create the ultra-high temperatures and densities needed for particle production. As the matter expands into the new universe, it cools, nuclei form, atoms emerge, and eventually gravity pulls matter together into the first stars and galaxies. From inside this new universe, looking backward in time, the expansion appears to originate from an initial hot, dense state, what we call the Big Bang. The beauty of this model is that it solves multiple problems simultaneously. First, it eliminates singularities. Torsion prevents infinite densities from forming, removing the mathematical pathology that plagued classical black hole theory. Second, it explains the Big Bang's origin. We don't need to explain how a singularity formed in the first place. Our Big Bang was the white hole end of a black hole in a parent universe. The initial conditions of our cosmos were simply the final conditions of whatever matter collapsed to form the parent black hole. Third, it provides a natural mechanism for cosmological natural selection. Each black hole creates exactly one new universe. The constants in that universe depend on how the transition through the wormhole affects quantum fields and particle properties. White holes have been theoretically predicted since the 1960s but never observed. They're the time-reverse solutions to Einstein's equations. If black holes have event horizons from which nothing escapes, white holes have event horizons into which nothing can fall. They're sources rather than sinks. Matter and energy pour out of them. But no white hole has ever been detected in our universe, which initially seems to contradict Poplawski's theory. If every black hole connects to a white hole, where are they? The answer is topology. The white hole exists, but it's in a different universe. The Einstein-Rosen bridge doesn't connect two regions of our spacetime. It connects our spacetime to a completely separate spacetime on the other side. When you fall into a black hole in our universe, you don't emerge from a white hole somewhere else in our universe. You emerge from a white hole that is the initial state of an entirely new universe. From that universe's perspective, there's no visible white hole now. There was one 13.8 billion years ago when their universe began. They call it the Big Bang. Just as we have a Big Bang in our past, they have one in theirs. And that Big Bang, which we interpret as a singularity that our physics cannot describe, is actually the white hole endpoint of the wormhole connecting their universe to ours through a black hole. This creates a stunning picture of cosmic structure. Every universe contains black holes. Each black hole is a wormhole, Each wormhole connects to a white hole that appears as the Big Bang of a new universe. That new universe expands, forms structures, creates stars, and eventually those stars collapse into black holes. Each of those black holes spawns another universe. The structure is self-generating, self-perpetuating, infinite in extent. There's no first universe, no ultimate parent, no beginning to the cascade, just an eternal network of universes connected through black holes, each one giving birth to countless offspring. Our universe would not be special. We exist inside a black hole that formed when a massive star collapsed in a parent universe we can never observe. The matter we're made of, every atom in every star and galaxy, came through the wormhole when our parent black hole formed. Our Big Bang was their stellar collapse, and every black hole we observe is doing the same thing in reverse, creating new Big Bangs in new universes that will themselves form stars and black holes and continue the process. The Milky Way's 100 million stellar black holes, 100 million new universes, the supermassive black hole at our galactic center, another universe, possibly far larger than ours given the enormous mass involved. Poplawski's theory makes predictions. The angular momentum of the parent black hole should affect the offspring universe's properties. Our universe has a slight preference for one direction of rotation in large-scale structure, a cosmic axis that some observations have hinted at. This could be inherited from the parent black hole's spin. The spectrum of primordial density fluctuations, the pattern of slightly denser and less dense regions in the early universe that eventually became galaxy clusters and voids, could preserve information about conditions in the wormhole throat. And the fundamental constants, if they're set by how quantum fields transition through the bridge, should cluster near values that maximize black hole formation, exactly as Smolin's theory requires. The two theories complement each other. Smolin explains why constants have the values they do through selection. Poplawski explains the physical mechanism that implements the selection. The theories we've discussed so far assume one universe spawns from each black hole. But Jaume Garriga's work suggests something far more extravagant. In a 2016 paper titled Black Holes and the Multiverse, Garriga demonstrated that supercritical black holes, those whose interiors inflate faster than the external universe expands, don't create just one offspring universe. They create infinitely many. Inside these black holes, eternal inflation occurs, continuously nucleating bubble universes of every vacuum state permitted by particle physics. The space-time structure becomes infinitely complex, with inflating regions connected by wormholes, spawning an endless cascade of pocket universes. The key concept is eternal inflation, a scenario proposed in the 1980s by Alan Guth and others. Standard inflation suggests the early universe underwent a brief period of exponential expansion, smoothing out irregularities and setting initial conditions for the hot Big Bang. But in many inflationary models, once inflation starts in a region, quantum fluctuations can cause it to continue in some patches, even as it ends in others. The inflating patches grow exponentially, generating vast volumes of space still undergoing inflation, while other regions exit inflation and evolve into universes like ours. This process never globally ends. It continues eternally into the future, constantly producing new regions that exit inflation and form pocket universes. Garriga applied this to black hole interiors. When a sufficiently massive black hole forms, its interior can contain enough energy density to drive inflation. Instead of simply bouncing and forming one new universe, the interior inflates eternally. Within this inflating space, quantum fluctuations cause different regions to tunnel to different vacuum states. Each vacuum state represents a different configuration of fundamental fields, potentially with different effective laws of physics, different particle masses, different force strengths. As each region exits inflation, it forms a bubble universe with its own distinct properties. The mathematics reveals extraordinary structure. The eternally inflating interior connects to our universe through the black hole's event horizon, but it also develops internal wormhole connections between different inflating patches and between bubbles that have exited inflation. The topology is mind-bending. You have a multiply-connected spacetime where travel between different vacuum bubbles might be possible through wormhole networks, even though each bubble appears infinite and isolated from within. The entire structure grows without bound, becoming more complex as eternal inflation continues, nucleating more bubbles, creating more connections. This has profound implications. A single supermassive black hole in our universe, say the one at the center of the Milky Way, with 4 million solar masses, wouldn't house just one universe. It would house infinitely many, representing all possible vacuum states that particle physics allows. If string theory is correct, and there are 10 to the 500th possible vacuum configurations in the landscape, then inside one black hole, you'd eventually get bubbles corresponding to every one of those possibilities. Each bubble would be a complete universe, potentially infinite in size from its own internal perspective, with galaxies, stars, and possibly life, all existing in a region we perceive as a black hole a few million kilometers across. The disparity between internal and external perspectives becomes even more dramatic. From our universe, time inside the black hole appears frozen. Nothing that crosses the event horizon can send us information. The interior seems static, locked at the moment of formation. But from inside, time flows normally. In fact, it flows for eternity. An infinite amount of proper time elapses in the interior, while only finite time passes outside. This means the eternally inflating multiverse inside the black hole has infinite time to nucleate infinite bubbles, explore infinite vacuum configurations, and develop infinite complexity, all while we observe the black hole aging normally. Through Hawking radiation over trillions of years, Garriga's model predicts that most of the multiverse's volume exists inside supercritical black holes. Our universe, the one we observe, would be atypical. We'd be living in a region that's not inside a black hole, or at least not inside a supercritical one undergoing eternal inflation. Most observers, if we count them by the volume of space they inhabit, would find themselves in bubble universes nested deep inside inflating black hole interiors, connected to external universes through long chains of wormholes. This raises questions about probability and observation. If most of the multiverse consists of bubbles inside black holes, and those bubbles have different physical constants and laws, how do we predict what typical observers should experience? This is the measure problem in eternal inflation, one of the deepest puzzles in theoretical cosmology. Different ways of counting observers give different predictions for what we should expect to see. Some measures predict we're in a typical bubble. Others predict we're in a highly atypical one. The lack of a unique prescription for assigning probabilities makes testing the theory challenging. But testable predictions exist. If our universe itself formed inside a black hole, there might be observable signatures. The cosmic microwave background, the radiation left over from our early universe, could contain imprints of the wormhole throat we emerge from. Deviations from perfect isotropy, unexpected correlations at large scales, or anomalies in the polarization pattern might reveal our origin inside a parent black hole. Several potential anomalies have been detected, including the cold spot and the axis of evil, large-scale features that don't match standard cosmological predictions. Whether these are statistical flukes or genuine signals of exotic origin remains controversial. Additionally, the distribution of black hole masses in our universe might reveal whether they undergo eternal inflation internally. Supercritical black holes require specific mass ranges and formation conditions. If we observe mass gaps or clustering that correlates with criticality thresholds, it would support the theory. Recent observations of black hole mergers via gravitational waves have revealed unexpected mass distributions, including potential gaps and peaks that don't match simple stellar evolution predictions. These could be hints of underlying physics related to black hole universes, though conventional explanations remain viable. Garriga's multiverse is fractal and self-similar. Universes contain black holes that contain universes that contain black holes, infinitely nested. But it's also diverse. Each level can have different vacuum states, different constants, different dimensionality potentially. The structure is both infinite in extent and infinite in variation, exploring every possibility allowed by fundamental physics across an eternally growing network of causally connected pocket universes. In 2025, a team led by Enrique Gastañaga at the University of Portsmouth published research that brings black hole cosmology into sharp focus with testable predictions. Their black hole universe model proposes that our observable universe emerged not from a singular Big Bang, but from the gravitational collapse of matter in a parent universe, followed by a quantum bounce inside the resulting black hole. This isn't just philosophical speculation. The model makes specific predictions about cosmic curvature and expansion rates that upcoming observations can verify or falsify. The key innovation involves applying quantum exclusion principles to gravitational collapse. In quantum mechanics, fermions like electrons and quarks obey the Pauli exclusion principle, which prevents them from occupying the same quantum state. At extreme densities approaching the Planck scale, this exclusion generates enormous pressure. Gastañaga's team demonstrated that when collapsing matter reaches a critical density, quantum exclusion pressure overcomes gravitational attraction. The collapse halts and reverses. The matter bounces. Critically, this bounce occurs entirely within general relativity, combined with fundamental quantum mechanics. No exotic fields required, no extra dimensions, no speculative physics beyond established theory. The calculations show that when a sufficiently massive, nearly homogeneous cloud of ordinary matter collapses in a parent universe and crosses its Schwarzschild radius, forming an event horizon, the interior doesn't proceed to a singularity. Instead, quantum pressure triggers a bounce at a specific radius determined by the density and gravitational constant. This bounce initiates exponential expansion that, from inside, appears identical to cosmic inflation, followed by normal expansion. The model explains several puzzles about our universe. First, why did the Big Bang happen? Standard cosmology treats the initial singularity as a boundary condition, something given without explanation. The black hole universe model provides a mechanism. The Big Bang was the quantum bounce following gravitational collapse in a parent universe? Second, why does the universe undergo two distinct phases of accelerated expansion, early inflation, and late-time dark energy acceleration? The bounce naturally produces both. The immediate post-bounce phase drives inflation. The residual bounce dynamics, combined with the geometry of the black hole interior, generate late-time acceleration without requiring mysterious dark energy fields. Third, why is the universe so close to spatially flat? Observations suggest the curvature parameter omega k is extremely close to zero, within a fraction of a percent. Standard inflation explains this by expanding a small region to enormous size, diluting any initial curvature. But the black hole universe model predicts slight positive curvature, a closed universe with omega k between negative 0.07 and 0. This reflects the initial overdensity that triggered the collapse. The cloud that collapsed to form the parent black hole had slightly more matter than average, creating a slight curvature that persists through the bounce and expansion. Current observations cannot distinguish between perfectly flat and slightly closed at this precision level, but upcoming missions like Euclid might detect this signature curvature. The model also predicts specific expansion rates consistent with recent measurements. The Hubble tension, the discrepancy between different methods of measuring cosmic expansion, has puzzled cosmologists. Early universe measurements from the cosmic microwave background give one value. Late universe measurements from supernovae and galaxies give a higher value. The black hole universe model's predictions for expansion dynamics match the observations more closely than standard lambda CDM cosmology, potentially resolving the tension without invoking new physics. If we live inside a black hole, several questions arise. What does the parent universe look like? We cannot observe it. The event horizon prevents any information from crossing back. From the parent universe's perspective, our entire cosmic history plays out inside a black hole that formed and has been slowly evaporating through Hawking radiation. Trillions of years might pass in our universe while only millions pass outside. The time dilation is extreme and orientation dependent, based on the black hole's properties. Does the parent black hole rotate? If so, its angular momentum becomes a preferred axis in our universe. This could explain anomalies in the cosmic microwave background, including the axis of evil, a mysterious alignment of large-scale temperature fluctuations along a specific direction. Standard cosmology predicts perfect isotropy with no preferred directions. But if our universe inherited angular momentum from a rotating parent black hole, we'd expect slight deviations from isotropy aligned with that rotation axis. Several studies have detected such alignments, though their statistical significance remains debated. What happens at the boundaries of our observable universe? In standard cosmology, the universe extends far beyond what we can see, possibly infinitely. In the black hole universe model, there's an actual boundary. The black hole's interior horizon, where our expanding spacetime connects to the parent universe through the wormhole throat. This boundary lies beyond our observable horizon, approximately 47 billion light-years away in comoving distance, so we cannot see it directly. But its existence imposes constraints on global topology and might affect the largest observable scales. Can we ever escape? No. From inside the event horizon, all paths lead further into the black hole interior, which is our expanding universe. Traveling outward in space, doesn't take you closer to the parent universe. It takes you further into our own cosmic future. The event horizon isn't a place in our space. It's in our past, at the moment of the Big Bang bounce. You cannot travel back through it any more than you can travel backward in time to before you were born. The Portsmouth team emphasizes testability. Within the next decade, observations from Euclid, the Vera Rubin Observatory, and next-generation cosmic microwave background experiments should measure spatial curvature with sufficient precision to detect the predicted slight positive value if it exists. Measurements of expansion rates at different epochs will test the model's predictions about how acceleration evolves. Gravitational wave observations from merging black holes might reveal mass distributions that reflect black hole universe formation conditions. The theory makes contact with observation in ways that allow definitive tests. If confirmed, the implications are staggering. The Big Bang wasn't a beginning, but a transition. Our universe has a parent, and we're living in its black hole. Every black hole we observe could house universes as rich and complex as ours. The structure of reality is nested, layered, infinite in both directions. No ultimate origin, no first cause, just gravity and quantum mechanics, creating cosmos after cosmos in an eternal cycle. How do we test whether black holes actually contain universes? These theories sound elegant, but science demands evidence. Fortunately, several testable predictions distinguish black hole cosmology from standard models. The first involves primordial black holes, objects formed in the first fraction of a second after the Big Bang from density fluctuations in the early universe. If these exist in sufficient numbers, they could constitute a significant fraction of dark matter, the mysterious substance comprising 85% of the universe's mass. Primordial black holes would have masses ranging from microscopic to hundreds of solar masses, depending on when and how they formed. Unlike stellar black holes created from collapsing stars, primordial black holes form directly from compressed regions of spacetime in the early universe. If every black hole spawns a universe, then every primordial black hole that formed in our cosmic infancy created its own offspring universe. The number and mass distribution of primordial black holes directly tests cosmological natural selection. Smolin's theory predicts our universe should be optimized to produce black holes efficiently. If primordial black holes exist in large numbers, it supports the idea that universes with these conditions reproduce more successfully. Observations are closing in on this question. The Subaru telescope in Hawaii conducted a 7-hour observation of the Andromeda galaxy, searching for microlensing events caused by primordial black holes in the mass range between 10 to the negative 14 and 10 to the negative 9 solar masses. Microlensing occurs when a compact massive object passes between us and a background star, temporarily magnifying the star's light due to gravitational lensing. The duration and intensity of the magnification reveal the lensing object's mass. The Subaru observations found one candidate event, but determined that primordial black holes in this mass range cannot constitute all of dark matter. However, other mass ranges remain viable. LIGO's gravitational wave detections provide another window. The black hole mergers detected since 2015 have revealed unexpected mass distributions. Several black holes fall in the 30 solar mass range, at the upper edge of what stellar collapse should produce. Some researchers propose these could be primordial black holes formed in the early universe rather than from dying stars. If confirmed, it would demonstrate that our universe did produce black holes through non-stellar mechanisms, consistent with being optimized for black hole formation. The mass spectrum of detected black holes compared to theoretical predictions could reveal whether our constants truly maximize black hole production. The cosmic microwave background offers crucial tests for whether we live inside a black hole. If our Big Bang was actually a quantum bounce inside a parent black hole, the properties of that parent should leave imprints. A rotating parent black hole would impose a preferred axis on our universe, breaking perfect isotropy. Several anomalies in the CMB hint at such asymmetries. The axis of evil refers to unexpected alignments of temperature fluctuations at the largest observable scales. The cold spot, a region colder than expected by chance, could represent a signature of the wormhole throat connecting us to the parent universe. These anomalies are statistically weak, and conventional explanations exist, but they're precisely what black hole cosmology predicts. Spatial curvature provides the most definitive test. Standard inflation predicts the universe should be spatially flat to extreme precision, with the curvature parameter omega k indistinguishable from zero. The black hole universe model predicts slight positive curvature, omega k between negative 0.07 and 0, inherited from the overdensity that collapsed to form the parent black hole. Current measurements from Planck satellite data constrain omega ISA to be within a few percent of zero, but cannot distinguish between perfectly flat and slightly closed. The Euclid Space Telescope, launched in 2023, will measure spatial curvature with 10 times better precision. If it detects positive curvature in the predicted range, it would strongly support the black hole universe hypothesis. Expansion rate measurements test the model's dynamics. The Hubble tension, the mismatch between early and late universe expansion rate measurements, challenges standard cosmology. The black hole universe model's predictions for how expansion evolves match observations more closely than lambda CDM in some parameter ranges. If refined measurements continue to favor the black hole model's expansion history, it would shift the balance of evidence. Additionally, observations of how structures formed at different cosmic epochs constrain the universe's evolution. The model predicts specific timelines for structure formation based on bounce dynamics that differ subtly from standard inflation. Finally, gravitational wave astronomy might detect echoes or anomalies in black hole merger signals if the black holes contain universes. The ring-down phase, when a newly merged black hole settles into equilibrium, should match general relativity's predictions precisely if black holes are simple vacuum solutions. But if interiors contain complex structure, quantum bounces, or nascent universes, deviations might appear. Current detectors lack sensitivity to see such subtle effects, but future observatories like LISA, the space-based gravitational wave detector, or Einstein telescope, the next-generation ground detector, might resolve them. These tests won't happen overnight. Observational cosmology advances incrementally, requiring years of data collection and analysis. But the crucial point is that black hole cosmology makes contact with observation. It's not pure speculation isolated from evidence. Within the next decade, measurements of curvature, black hole populations, and CMB anomalies will either support or challenge the theory. Science proceeds by testing bold ideas against reality. Black hole universes are bold. Now we discover if they're real. One of the most radical implications of black hole cosmology involves dark matter. the invisible substance that dominates the universe's gravitational landscape. We know dark matter exists because galaxies rotate faster than visible matter alone can explain. Galaxy clusters hold together with more gravitational binding than their visible stars and gas provide. Gravitational lensing reveals mass distributions that far exceed what we can see. Yet despite decades of searching, no dark matter particle has been directly detected. What if we've been looking in the wrong place? What if dark matter isn't a particle at all, but gravity leaking from baby universes inside black holes? This concept emerges from the topology of black hole interiors connected to new universes. When matter falls into a black hole and bounces into a new expanding universe, that new universe contains mass and energy distributed across vast volumes of space from its internal perspective. Galaxies form, stars ignite, matter clusters gravitationally. All of this mass generates gravitational fields. But gravity, unlike other forces, isn't confined to a single space-time region. In theories with wormhole connections between universes, gravitational effects can propagate through the connecting throat. Think about what this means. A supermassive black hole in our galaxy contains, according to these theories, an entire universe expanding internally. That universe might contain trillions of galaxies, each with billions of stars, all generating gravitational fields. Those gravitational fields exist in their space-time, but geometrically connect to ours through the wormhole throat at the black hole. The gravity doesn't stay contained in the baby universe. It leaks. And from our perspective, observing the region around the black hole, we detect gravitational effects stronger than the black hole's mass alone can explain. We call this excess gravity dark matter. This would explain why dark matter appears distributed in halos around galaxies. If supermassive black holes at galactic centers contain baby universes, the gravitational leakage would spread outward from the black hole, creating an extended gravitational influence surrounding the visible galaxy. The distribution would match dark matter halo profiles. The strength would scale with the black hole mass. And observations confirm that more massive galaxies, which host more massive central black holes, also have more dark matter. The correlation makes sense if dark matter is gravitational leakage from universes inside those black holes. It would also explain dark matter's unusual properties. Dark matter doesn't emit light, doesn't absorb light, doesn't interact electromagnetically at all, but it responds to gravity and generates gravitational fields. If dark matter is gravity from another universe, these properties are exactly what we'd expect. Gravity crosses between universes through the wormhole connection, but electromagnetism, the strong force, and the weak force don't. They're confined to their respective space-time regions. Only gravity, which is space-time curvature itself, rather than a force propagating through space-time, can leak between causally disconnected regions. The theory makes testable predictions. Dark matter distributions should correlate precisely with black hole locations and masses. Galaxies without supermassive black holes should have correspondingly less dark matter, while galaxies with unusually massive black holes should have dark matter halos exceeding standard predictions. Additionally, the fine structure of dark matter halos might reveal information about structure formation in baby universes. If baby universes contain clustered matter distributions, the leaked gravity would show corresponding structure. Observations of dark matter substructure could, in principle, reveal details about galactic distributions in universes we cannot directly observe. Primordial black holes strengthen this connection. If the early universe produced numerous small black holes, and each contains a baby universe, then the combined gravitational leakage from billions or trillions of primordial black holes could account for the diffuse dark matter detected throughout cosmic voids and in galactic halos. The Subaru observations constraining primordial black hole abundances in certain mass ranges are directly testing this possibility. If future observations detect primordial black holes in the right abundance and mass distribution, it would support the baby universe dark matter hypothesis. However, challenges exist. Most dark matter models require it to be cold, moving slowly compared to light speed, to explain structure formation. Gravitational leakage from rapidly expanding baby universes might produce effects inconsistent with cold, dark matter, unless specific conditions are met regarding the universe's expansion rates and matter distributions. Additionally, dark matter must have been present in the early universe, long before most stellar mass black holes formed. This requires primordial black holes, or supermassive black holes, to have formed extremely early, which is possible, but not yet confirmed. The hypothesis also faces competition from conventional dark matter candidates. WIMPs, weakly interacting massive particles, remain plausible despite negative detection results so far. Axions, ultralight hypothetical particles, could explain some observations. Modified gravity theories attempt to eliminate dark matter entirely by adjusting how gravity works at galactic scales. Distinguishing between these possibilities requires precise observations of how dark matter distributes spatially and how it behaves dynamically across different environments. Nevertheless, the gravity leakage hypothesis offers something unique. It connects dark matter to black holes and multiverses, three major mysteries in modern physics, through a single elegant mechanism. If true, it would mean the invisible mass dominating our universe isn't mysterious particles lurking in the void. It's ordinary matter in other universes, revealing its presence through the only force that transcends the boundaries between realities: gravity. If cosmological natural selection is correct, our universe should be fine-tuned, not for life, but for black hole production. This makes a stunning prediction. The 21 fundamental constants governing physics should be optimized to maximize the number of black holes formed over cosmic history. Any small change to these values should reduce black hole production. We live in a universe descended from countless generations of black hole-producing ancestors, inheriting parameters refined across billions of iterations to excel at stellar collapse. Consider the fine-tuning problem that has puzzled physicists for decades. Why is the cosmological constant so small? Its measured value is approximately 10 to the negative 122 in Planck units. Theory suggests it should be vastly larger, around 1 in Planck units, making it the most precisely fine-tuned constant we know. A larger cosmological constant would accelerate cosmic expansion too rapidly, preventing galaxies from forming. No galaxies means no stars. No stars means no stellar mass black holes. Our tiny cosmological constant allows the universe to expand slowly enough for gravity to pull matter together into structures that eventually collapse into black holes. It's exactly what cosmological natural selection predicts. The strong nuclear force provides another example. It binds quarks into protons and neutrons with efficiency epsilon equal to 0.007. This means 0.7% of the mass converts to binding energy when hydrogen fuses to helium. If epsilon were slightly lower, around 0.006, fusion wouldn't generate enough energy to sustain stars. They'd collapse immediately. never reaching stable main sequence phases, drastically reducing the number that eventually become black holes. If epsilon were slightly higher, around 0.008, hydrogen would fuse so efficiently that primordial nucleosynthesis would convert most hydrogen directly into heavier elements in the early universe. Stars would burn hotter and faster, potentially bypassing mass ranges that produce black holes. The observed value sits in a narrow range optimizing stellar evolution for black hole formation. The mass difference between neutrons and protons demonstrates similar tuning. Neutrons are 1.3 MeV heavier than protons. If this difference were just slightly larger, neutrons would decay too quickly to form atomic nuclei, eliminating chemistry and complex matter. If it were slightly smaller or reversed, protons would decay into neutrons, again, preventing complex structures. The observed value allows neutron stars to exist as stable configurations while also permitting stars massive enough to exceed the Tolman-Oppenheimer-Volkoff limit and collapse into black holes. It threads a precise needle between stability and collapse. Martin Rees identified 6 dimensionless constants as particularly critical for cosmic structure. The ratio n of electromagnetic to gravitational force strength between protons equals approximately 10 to the 36. The density parameter omega equals approximately 1. The amplitude q of density fluctuations equals approximately 10 to the negative 5. Each parameter influences how efficiently the universe produces black holes. Change n and stellar structure changes, affecting which stars collapse. Change omega and the universe might recollapse before stars form or expand so fast structures never emerge. Change q and either no structures form or everything collapses into black holes immediately, potentially reducing total production over cosmic time. Cosmological natural selection predicts our universe sits at a local maximum in the parameter space for black hole production, not necessarily the global maximum, which might require scanning all possible values, but a local optimum where small perturbations in any direction reduce efficiency. Fred Adams calculated how varying several constants affect stellar populations and black hole formation rates. For many parameters, our universe appears near local maxima. This doesn't prove the theory, but provides precisely the correlation it predicts. Recent work by Joseph Bramante and Nirmal Raj reveals another remarkable possibility. They demonstrated that dark matter with specific minimal properties could convert the majority of baryonic matter in galaxies into black holes over timescales of hundreds of trillions of years. This process occurs through dark matter particles accumulating inside stars and catalyzing their collapse into black holes much earlier than normal stellar evolution would allow. If this mechanism operates, then universes with these dark matter properties would produce vastly more black holes than universes without them, gaining enormous reproductive advantages in the cosmological natural selection framework. The timescale is crucial. 100 trillion years exceeds the current age of the universe by more than 7,000 times. Main sequence stars will have long since burned out. White dwarfs will dominate stellar populations. But if dark matter slowly accumulates in these remnants and triggers collapse, the universe would experience a second era of black hole formation far more productive than the first. A universe optimized not just for immediate black hole production, but for maximized production across its entire future, would naturally evolve properties enabling this process. This creates a testable prediction. The properties of dark matter should correlate with what's required to maximize long-term black hole formation. If dark matter is eventually identified and its properties measured, cosmological natural selection predicts those properties will be precisely tuned to enable efficient conversion of baryons into black holes over cosmic timescales. No other explanation for dark matter properties makes this prediction. It's a unique signature of universes evolved through black hole reproduction. Fine-tuning traditionally invokes either design or anthropic selection. Cosmological natural selection offers a third option: natural selection through reproduction. We're fine-tuned for black holes because our ancestors were, and their ancestors before them, across endless generations of cosmic evolution. Life emerges as a side effect, a byproduct of conditions that also favor stellar collapse. We exist because the universe is good at making black holes, not because it was made for us. Step back and contemplate the full structure. If every black hole contains a universe, and every universe contains black holes, the architecture of reality becomes infinitely nested. Russian dolls made of space-time. Our universe exists inside a black hole in a parent universe. That parent universe exists inside a black hole in a grandparent universe. This continues infinitely upward, with no ultimate container, no base reality, no largest universe that holds all others. And it continues infinitely downward. Every black hole in our universe contains offspring universes. Every black hole in those offspring contains more. The nesting never ends. This fractal structure defies our intuitions about inside and outside, container and contained. From our perspective, a stellar mass black hole is tiny, just kilometers across. But from inside, it's an entire expanding universe potentially infinite in extent. The supermassive black hole at the center of the Milky Way appears finite from here. Inside, it might contain trillions of galaxies spread across billions of light years. Scale becomes relative. Size loses absolute meaning. What's enormous from one reference frame is microscopic from another. Consider what this means for the concept of boundaries. Our observable universe has an edge, the cosmic horizon approximately 47 billion light-years away in co-moving distance. Beyond that horizon, space expands faster than light can travel toward us, making further regions forever unobservable. But in the black hole cosmology framework, there's also a boundary in a different sense. The event horizon connecting our universe to the parent universe exists in our past, at the moment we interpret as the Big Bang. That boundary isn't a place in space. It's a moment in time. The edge of our universe in one direction is temporal, not spatial. Meanwhile, the black holes we observe represent boundaries in the opposite direction. When matter crosses their event horizons, it leaves our spacetime and enters descendant universes. Those boundaries are also temporal from our perspective. Once something falls in, it's gone from our present. It exists only in the future interior of the black hole, which from inside experiences as its own present. Time and space exchange roles at event horizons, making the inside-outside relationship even stranger. The structure has no beginning, no first universe that started the cascade. Every universe has a parent, which has a parent, extending infinitely into the past. This eliminates the cosmological first cause problem. We don't need to explain where the first universe came from, because there was no first universe. The chain of causation extends eternally backward. Each universe's origin is simply the black hole formation event in its parent. No moment where something came from nothing. No violation of ex nihilo nihil fit. just continuous generation through gravitational collapse and quantum bounces. It also has no end in the traditional sense. Even if individual universes eventually die through heat death or big rip expansion, their black holes have already spawned new universes that continue evolving. The death of one universe is the birth of countless others. Cosmic reincarnation operates automatically through gravity. The multiverse as a whole never dies because dying universes are continuously replaced by newborn ones emerging from their black holes. Existence perpetuates itself through reproduction at cosmic scales. The philosophical implications are staggering. Reality becomes fundamentally bootstrapped. Each level of the structure depends on levels above and below, but the whole requires no external support, no prime mover, no ultimate ground of being. It's self-causating, self-sustaining, self-explaining. The laws of physics at each level emerge from the parameters inherited from parent universes and quantum fluctuations during the bounce transition. No legislator wrote the laws. They evolved through selection across generations. This resolves the fine-tuning problem in the most elegant way possible. Constants aren't fine-tuned by design. They're fine-tuned by evolution. Universes with constants that produce many black holes have many descendants. Universes with constants that produce few black holes have few descendants. Over infinite generations, the population becomes dominated by fine-tuned lineages. We observe fine-tuning not because we're special, but because we're typical descendants of successful ancestors. It also transforms the meaning of cosmic death. The heat death of the universe, when entropy maximizes and all usable energy dissipates, has been called the ultimate cosmic tragedy. Stars burn out, black holes evaporate. Everything decays into cold, dark, eternal equilibrium. But if black holes spawn universes, heat death becomes rebirth. The moment of maximum entropy, when all matter has fallen into black holes, is simultaneously the moment of maximum creation. Each black hole is a new beginning. Our universe's death will be other universes' big bangs. Death and birth are the same process viewed from different sides of event horizons. The Russian doll structure means we're never at the center and never at the periphery. Every universe is intermediate. Above us, larger universes contain the black hole we inhabit. Below us, smaller universes inhabit the black holes we observe. There's no privileged level, no base reality more real than others. Each universe is equally valid, equally existent, equally ignorant of its broader context. We're embedded in an infinite hierarchy where every level thinks itself fundamental while being merely one layer in an endless stack. This is the multiverse taken to its logical extreme. Not parallel universes side by side, but nested universes connected through black holes, infinitely deep in both directions with no beginning, no end, no edges, and no outside. Just gravity and quantum mechanics, generating cosmos after cosmos in an eternal recursive structure that explains itself through natural selection and needs nothing external to account for its existence. So what does it mean for humanity to discover that every point of total collapse might be a point of infinite creation? That every black hole we observe through our telescopes could harbor universes as vast and complex as our own? That the ultimate symbol of cosmic death is simultaneously the ultimate engine of cosmic birth? It means we've been fundamentally wrong about the nature of endings. What we call destruction is transformation. What we call annihilation is genesis. The universe doesn't end at black holes. It begins there. This realization transforms our understanding of existence itself. For centuries, we've contemplated our cosmic insignificance. We're on a planet orbiting an ordinary star in a galaxy containing hundreds of billions of other stars. In a universe with trillions of galaxies, we're tiny, ephemeral, irrelevant at cosmic scales. But if black hole cosmology is correct, that insignificance multiplies infinitely. We're not just in one universe among trillions of galaxies. We're in one universe among infinite universes, nested infinitely deep in both directions. The Milky Way's 100 million stellar mass black holes. Each could contain entire cosmoses with their own observers contemplating their own insignificance. Yet paradoxically, this makes existence more meaningful, not less, because it reveals that the universe isn't winding down toward eternal death, it's regenerating. Every generation of stars creates a new generation of universes. The process never stops. Reality perpetuates itself through the very mechanism we thought ended it. Black holes aren't cosmic executioners. They're cosmic midwives, delivering new realities into existence through gravitational collapse and quantum bounces. The circle of cosmic life operates on scales we never imagined. It also means our universe has a history deeper than the Big Bang. We're not the beginning. We're a chapter in a story with no first page. Our universe emerged from a black hole in a parent universe, that emerged from a black hole in a grandparent universe, extending infinitely backward. Every star you see at night, every galaxy detected by Hubble or James Webb, every atom in your body, passed through a wormhole connecting our reality to a parent reality we can never observe. Your existence depends on a stellar collapse that happened in another universe. You're made of matter that crossed an event horizon and bounced into this cosmos. And every black hole we create or observe continues that legacy. When a massive star in the Milky Way exhausts its fuel and collapses, it doesn't just die, it gives birth. Somewhere inside that event horizon, beyond the reach of any observation we could ever make, a new spacetime expands. New galaxies form, new stars ignite, perhaps new life emerges, asking the same questions we ask, contemplating their place in a cosmos they believe is the only one. They'll never know they exist inside what we call a black hole, just as we'll never know for certain that we exist inside a black hole in a parent universe. The topology of spacetime makes such knowledge impossible. Each universe is sealed inside its own causal domain, connected to others only through the boundaries we call event horizons. This is the multiverse theory that emerges from taking gravity seriously, not from quantum mechanics or string theory, though those might support it, not from philosophy or theology, from Einstein's equations combined with quantum principles applied to the most extreme gravitational conditions nature produces. The mathematics suggests it. The logic demands it. And upcoming observations might confirm it. Measurements of spatial curvature, black hole populations, cosmic microwave background anomalies, all could reveal signatures of our black hole origin within the next decade. If confirmed, it would represent one of the greatest revelations in human history. Comparable to realizing Earth isn't the center of the solar system, that the solar system isn't the center of the galaxy, that our galaxy is one among countless others. This would be the final step. Our universe isn't the entirety of existence. It's one node in an infinite network, connected to parent and offspring cosmoses through black holes, part of an eternal structure that generates itself through gravity and quantum mechanics, requiring no external creator, no ultimate beginning, no final end. What black holes do, then, is perhaps the most profound thing physics has ever suggested. They don't destroy information, energy, and matter. They transform it. They transfer it to new contexts, new universes, new opportunities for complexity and structure, and perhaps even consciousness to emerge. They prove that endings and beginnings are the same event viewed from different perspectives, that death and birth are two sides of one process, that the universe operates on principles of eternal return, cosmic reproduction, and natural selection, at scales that make biological evolution seem like a minor detail. We live in a universe that came from a black hole and will create countless black holes that spawn countless more universes. We're embedded in an infinite fractal of nested realities, each one as real and complete as any other, all connected through gravity, all evolving through selection, all part of a structure that explains itself without needing anything external. This is what black hole cosmology reveals, not just science, not just mathematics, but a vision of existence as fundamentally creative, endlessly regenerating, and infinitely more profound than we ever imagined. Every black hole contains another universe, and that changes absolutely everything.